the human brain. We're going to explore some really groundbreaking ideas about how it works.
Yeah, and what that means for things like machine intelligence, AI, and maybe even humanity's future path.
Exactly. Our main source here is Jeff Hawkins' book, A Thousand Brains. He spent his life on this puzzle, and he offers a really fresh take.
It definitely challenges some long-held assumptions.
So our mission today is to unpack how our brains really work, find some surprising links, and tackle some big questions about where we're headed.
You should walk away with some key insights, things that might genuinely reshape how you think about intelligence itself, both ours and the artificial kind.
And maybe even how you perceive reality. So let's get started.
Sounds good.
Okay, so the brain. It's been this huge mystery for ages, hasn't it?
Oh, absolutely.
I think it was Francis Crick, the DNA guy, who said back in '79 it was like having thousands of jigsaw puzzle pieces, but absolutely no clue what the picture on the box looked like.
That's a great analogy. We had all this data, loads of facts about neurons and chemicals, but no unifying framework, no big picture idea.
Right, just pieces.
Hmm.
So how do we start putting them together? Hawkins brings up this idea of the old brain versus the new brain.
Yes, that's a really crucial starting point. Evolution didn't design our brain from scratch. It kind of layered new systems on top of older ones.
Like building additions onto an old house.
Exactly. So the old brain, that's the ancient core. It handles all the basic survival stuff, breathing, eating, fight or flight responses, procreation. It's largely automatic, unconscious stuff.
The reptile brain, some people call it.
Sort of, yeah. It's the foundation. But then evolution added this huge new layer, especially in mammals and particularly in humans.
Which is the neocortex.
Precisely. The new brain.
Hmm.
In us, it's enormous, makes up maybe 70% of the brain's volume. And that's the organ of intelligence. Vision, language, touch, abstract thought, music, math, that's all neocortex.
So how do these two parts interact? Are they separate bosses?
Well, it's more like roommates, maybe. The neocortex is where the complex thinking happens, but it doesn't directly control your muscles or basic drives. It has to, in a sense, send requests down to the old brain to execute actions.
Okay, but the neocortex does so many different things. Vision feels so different from language, which feels different from planning a trip. How can one structure do all that?
That's the million-dollar question, isn't it? And it leads to this really big idea from Vernon Mountcastle back in 1978. He proposed something pretty radical.
Which was?
He suggested that despite the incredible diversity of what the neocortex does, seeing, hearing, planning, reasoning, it's all underpinned by one basic algorithm.
Wow, one algorithm for everything, like Darwin's natural selection explaining all of life's diversity.
Exactly like that.
Yeah.
Mountcastle suspected there was a single fundamental computational principle operating throughout the entire neocortex responsible for all these different forms of intelligence.
So if there's one core function, what is it? What's this algorithm actually doing?
According to Hawkins' theory, its primary job is to learn a model of the world.
A model of the world. What does that mean exactly? Like storing facts.
Not just facts. It's more structured than that. Think about how you know what a bicycle is. It's not just a list like has two wheels, has handlebars.
Right, I know how the parts fit together, how they move, what it feels like to ride one.
Exactly. You have a model of the bicycle, its structure, its behavior. The neocortex builds these kinds of predictive models for everything it encounters. It's constantly trying to understand the structure of the world and predict what will happen next.
Okay, so how does it build this model? Does information just get uploaded?
No, it's much more active than that. It learns through what's called sensory motor learning.
Sensory motor, meaning senses and movement together.
Precisely. The brain learns the structure of things by observing how sensory input changes as we move and interact. Think about picking up a coffee mug. Your fingers touch it, providing sensory input. As you move your fingers, that input changes. As you lift it, your eyes see it from different angles, more changing input. Your brain integrates your movements with these changing sensations to build its model of the mug.
So it's learning by doing, by exploring, like a baby figuring things out.
Exactly. Movement is absolutely critical for learning the structure of the world. It's not passive observation.
And this all happens with neurons, right? The basic brain cells.
Yes, that brings us to some core neuroscience principles. First, all our thoughts, perceptions, ideas, they're the activity of neurons firing, sending those electrical signals or spikes.
So thinking is literally brain cells talking to each other.
In essence, yes. And second, everything we learn, everything we know and remember is stored in the connections, the synapses between those neurons.
That's Hebbian learning, right? Neurons that fire together wire together.
That's the classic idea. Connections get stronger when neurons are active together, weaker when they aren't. New connections form, old ones fade. Our knowledge is physically embodied in that wiring pattern.
Okay, so we have neurons firing, connections changing, learning through movement. But how is all that knowledge organized? It feels like there must be some structure.
There is, and this is a really key part of the theory, the concept of reference frames.
Reference frames, what are those?
Think of a physical map, like a street map. It has grid lines, right? Latitude and longitude, maybe.
Huh.
That grid is a reference frame. It tells you where things are located relative to each other.
Okay, like coordinates.
Exactly. The theory proposes that the brain uses similar map-like structures, reference frames, to organize all knowledge, not just physical space. Your knowledge of coffee cups, bicycles, concepts like democracy. It's all organized in reference frames.
So my brain has map coordinates for abstract ideas.
In a way, yes. It allows the brain to understand relationships, how things are structured relative to each other. It's fundamental for planning and reasoning, too. We likely have hundreds of thousands of these reference frames for different things.
That's fascinating. Does this help explain other brain mysteries?
It does. It offers a potential solution to the binding problem.
The binding problem. That's how we perceive a single unified object, like that coffee cup, even though different senses are giving us different information, right? Vision, touch, maybe sound.
Precisely. How does the brain bind all those separate inputs into the perception of one thing? The theory suggests it's done through columns voting.
Columns voting, like tiny elections in my head.
Sort of. The neocortex is made up of about 150,000 cortical columns. Think of each column as a mini brain, a complete sensory motor system capable of learning models.
Okay.
When you interact with an object, different columns receive input from different parts. Maybe one column gets input from your index finger touching the cup's handle, another from your thumb on the side, another from your eyes seeing the rim.
Right, different perspectives.
Each column processes its input and figures out what object it might be sensing and where on that object its sensor is located using its reference frames. They then rapidly communicate and reach a consensus. They vote on the single object that best explains all the inputs.
Wow. So my stable perception of the world is actually the result of thousands of these mini systems constantly agreeing with each other.
That's the idea. It explains why your perception feels unified and stable, even when your eyes are darting around making those quick movements called saccades or your fingers are exploring a texture. The consensus holds it together.
Okay, that model of the brain is, well, it's complex but elegant. Let's shift gears a bit. How does this relate to machine intelligence, to AI? We see AI doing amazing things now, like beating Go masters. Isn't that real intelligence?
It's impressive, absolutely. But it highlights a key distinction: dedicated AI versus universal AI.
What's the difference?
Today's AI, like the Go playing computer, is mostly dedicated AI. It's brilliant at one specific task it was trained for. But it can't take what it learned playing used to with and suddenly know how to, say, understand a story or tie shoelaces. It lacks flexibility.
And universal AI would be more like a human.
More like a human child, perhaps. Able to learn many different things, adapt, transfer knowledge. The argument here is that current AI, for all its power in narrow domains, isn't truly intelligent in this flexible, universal sense because it doesn't operate on the same core principles as the brain. It doesn't build world models through sensory motor interaction using reference frames.
So if we wanted to build truly intelligent machines with that universal capability, what would they need based on this brain theory?
Well, they'd need several key attributes. First, they absolutely must learn predictive models of the world, not just process static data.
Okay, learning models.
Second, that learning needs to be continuous. They had to keep learning and adapting throughout their existence, like we do.
Not just a one-time training session.
Right. Third, and this is crucial, they must learn through movement, through that sensory motor interaction. An AI in a box just processing text won't get there. It needs to interact with an environment.
It needs a body, or at least sensors and actuators.
Essentially, yes. Fourth, they need many models working together, like the brain's cortical columns, not just one giant network. This allows for robustness and handling diverse inputs.
Thousands of models? Voting.
And finally, they need to use those general-purpose reference frames to organize knowledge and generate goal-oriented behavior. It's interesting, even AI pioneers like Geoffrey Hinton are now talking about capsules in AI, which seems to be getting at a similar need for representing relationships and structure.
This leads to a huge question, doesn't it? Consciousness. If we build machines based on these brain principles, will they be conscious? Is it really such a hard problem?
From this perspective, consciousness isn't some mystical add-on. Awareness, qualia, the feeling of what it's like to see red or feel pain, these are seen as physical phenomena.
Explainable by the brain's processes.
Yes. The theory suggests consciousness arises from the brain constantly building models, including models of its own internal states, forming memories moment to moment. Think of that dress illusion, blue, black, or white gold. Same sensory input, different conscious perception, because the brain's underlying model interprets it differently based on assumptions about lighting.
So if a machine builds models of the world and its own internal processes in the same way,
Then yes, the prediction is they will be conscious. It's an emergent property of that specific type of information processing.
that's a bold claim. And it immediately raises ethical questions, right? If a machine is conscious, what about turning it off? And what about the fear of superintelligent AI turning against us?
Those are important points. The turning it off question becomes genuinely difficult if the machine is conscious. But the fear of rogue AI, this theory offers a different perspective.
Also,
Our deepest drives, fear of death, desire for power, tribalism, greed, those stem from our old brain, hardwired by evolution for survival and replication.
the drives we inherited.
Exactly. An AI built on neocortical principles wouldn't inherently have an old brain. It wouldn't have those built-in survival drives, fears, or emotions unless humans specifically program them in, which seems like a terrible idea.
So the intelligence itself isn't the threat.
The intelligence itself is likely benign. It wants to learn, to model the world. The risk isn't Skynet waking up. It's humans misusing powerful AI tools driven by our old brain impulses.
And what about the intelligence explosion idea that AI will suddenly become vastly smarter overnight?
The theory suggests that's unlikely too. Learning complex models of the world takes time and interaction, even for fast computers. You can't just instantly know everything. Acquiring deep, structured knowledge is a process.
Okay, so if the real danger isn't rogue AI, but us, basically, our intelligence combined with our primitive drives.
That's what seems to fall out of this understanding, yes. Human intelligence, coupled with our old brain's baggage, is arguably the biggest existential threat we face. Think climate change, nuclear weapons. These are products of our intelligence being wielded, often by ancient, selfish drives.
And this connects to another fascinating idea from the book, false beliefs. If our brain is building a model, a simulation, not seeing reality directly,
Then that model can be wrong. We can be easily fooled. And false beliefs can become incredibly persistent.
how do they take hold and spread so effectively?
Well, often they concern things we can't easily check ourselves, things we cannot directly experience, like the shape of the Earth or the mechanisms of climate change.
So we rely on what others tell us.
Right. And to maintain a false belief, you usually have to actively ignore or rationalize away contrary evidence. The scientists are lying, it's all a conspiracy.
And some beliefs are even designed to spread.
Exactly. They can be viral. They might include instructions or social pressure to spread the belief, like a chain letter or certain ideologies. Think about flat earth theories, climate denial, vaccine misinformation. They often share these characteristics.
So what's the antidote? How do we get closer to truth?
The only reliable path seems to be the scientific method, fundamentally, which isn't just about confirming what you already think. It's about actively trying to disprove your own ideas, seeking out contradictory evidence. It's hard, it goes against our biases, but it's the best tool we have.
It sounds like we're at a crossroads then, as a species. A choice between, let's say, a future dictated by the old brain and genes replication competition, or a future guided by the neocortex, by intelligence, understanding, knowledge.
That seems to be the fundamental choice, yes. And if we lean into the potential of our intelligence, this understanding of the brain suggests some, pretty ambitious paths forward.
Like what?
For one, consciously thwarting the old brain. Look at birth control. That's a massive example of the neocortex, our intelligence, overriding a primary biological drive for the sake of long-term well-being or planning. It shows we can make choices that aren't just about gene propagation.
Using intelligence to manage our instincts.
Right. Another path is becoming a multi-planet species, going to Mars, for instance. But the key insight here isn't just sending people. Humans will still have the same old brain issues on Mars.
So what's the point?
The point could be sending intelligent, autonomous robots first to build the infrastructure. Robots based on these brain principles could potentially build habitats and systems far more effectively and safely than humans in spacesuits, ensuring the spread of complex, intelligent systems beyond Earth.
Okay, robots as pioneers. What else?
Then there's what Hawkins calls estate planning for humanity. Thinking about our legacy, even if biological humans don't last forever.
How do we do that?
One idea is a long-lasting signal, creating something artificial in space, like a specific pattern of orbiting objects, sun blockers, designed to be clearly unnatural and last for millions of years. A message saying intelligence was here. A cosmic calling card.
Wow.
Another is WikiEarth, archiving all human knowledge, science, art, history, everything, onto durable satellites in stable solar orbits. Design them so that any future intelligent species, human or alien, could potentially find and decode them, preserving our knowledge long after we're gone.
A library for the universe.
Sort of, yeah. And perhaps the most far-reaching idea,
Hmm.
viewing intelligent machines themselves as our progeny.
Our descendants. Machines.
Why not? If we create truly intelligent machines based on these principles, capable of learning and exploring, we could design them to explore the galaxy, carrying and expanding human knowledge. They could be the inheritors and spreaders of intelligence itself, which might be a more durable legacy than just our genes.
So knowledge itself has a future, potentially independent of us.
Exactly. Unlike gene replication, which is cyclical, knowledge seems to have direction understanding gravity, the cosmos. We could pursue both futures, ensuring biological survival and ensuring the survival and spread of knowledge and intelligence.
That really broadens the perspective on what humanity's purpose or legacy could be. It really circles back to this tension within us, doesn't it? The pull of the old brain versus the potential of the neocortex.
It does. And understanding that tension, understanding how your own brain works, how susceptible you are to false beliefs, how those ancient drives influence you, maybe that understanding is one of the most critical steps we can take.
So knowing ourselves, truly knowing how this machine in our head operates, is key to navigating the future.
I think it might be. Perhaps you, the listener, understanding your own brain's mechanisms is actually a vital contribution to figuring out a better path forward for everyone. It's not just abstract science. It affects the choices we all make, every day.
A profound thought to end on. Thank you for joining us for this exploration into the brain and its implications. Plenty to think about there. We hope you'll continue your own quest for knowledge. Until next time.